please feel free to get started if you're ready. Thank you.
Hello, my name is Changu Kang, and I have my teammates Rene, Dena, Anthony Spencer, and our topic was El-Gamal Cryptosystem and variants. So these are the summaries that we're going to be going over: biography, introduction, exchange of key Diffie-Hellman, El-Gamal principle, brute force attack, and a man in the middle attack, solution, conclusion, and references. So first off, Dr. Tar El-Gamal, an Egyptian cryptographer who developed the El-Gamal encryption, was born on August 18, 1955 in Cairo. Dr. El-Gamal has bachelor's in science from Cairo University, a master's and doctorate from Stanford. He is an author of public key cryptography algorithm, inventing the El-Gamal algorithm in 1984. He's now a director of engineering at RSA Security. El-Gamal is a public key encryption algorithm which uses an asymmetric key encryption algorithm and is based on the Diffie-Hellman key exchange. The disadvantage of El-Gamal is the ciphertext will be twice as long as the plain text, but on the other hand, the advantage is that it will give different ciphertext every time we encrypt it with the same plain text. So this is the diagram of how Diffie-Hellman key exchange works. To briefly go over this, Bob and Alice is used in the example. They both have a public key of A and B, the capital letters, and it will commonly have a large prime number of P, random integer of alpha, and since they have a random integer, that's why they will have a different encryption every time they run it. And this is the operating principle of El-Gamal. So Alice will choose some number R, computing e to the R mod n, and Bob will do the same, choosing some random number S, computing KB, and they'll be exchanging KA and KB. Alice computes K to the RB, Bob computing KS to the A. They will be exchanging A to the R mod n, which is basically the Diffie-Hellman key exchange protocol, but they will not be transmitting R nor S. After that, Bell will compute P as equals to A, R to the S times P mod n, at least decrypting that over 1 over A to the RS times C mod n.
Okay, so our team member just pretty much explained the driving principle behind it, El-Gamal. So let's look at an example. For instance, we could take, right here the prompt is encrypt and decrypt message 35 and use a public database, which is our pretty much our prime generator, which is 5, and modulo n, which is our prime number, right? So let's see how this works. As my teammate mentioned, Bob and Alice choose a random number. Bob chooses 8 and Alice chooses 13. Bob then calculates. So mind you, this is their what is this? This is their private keys. So in order to calculate their public keys, we could take Bob, right? Bob puts the prime generator, which is 5 to the power of 8. Mind you, again, 8 is his private key. So followed by modulo 89, which gives him 4. So this 4, as like I said, is his public key. So he sends this to Alice. Hey Alice, my number is 4. So, and now we're in Alice's shoes. She does the exact same thing pretty much. She takes the prime generator and puts it to the power of 13, which is her private key, followed by modulo 89 and gets 40. So Alice takes this 40 and sends it to Bob. Hey Bob, my number is 40. So now they both have shared their public keys, right? So with this, Bob can now calculate an encryption key. So he takes Alice's number, which is 40, and puts it to the power of 8, which is his private key, followed by modulo 89. this essentially gives him 16. So now Bob has an encryption key. So with this encryption key, he can now cipher the text. So what he does is we have our message P, which is 35, which is our plain text that we're trying to cipher. So the equation for that is 16 times 35. Again, the encryption key times the message, which is 35, followed by mod 89, gives them 26. So now 26 is our ciphertext. So Bob takes this and he sends this to Alice. Hey, Alice, 26 is the encrypted message. Okay, so now Alice wants to encrypt, right? I mean, decrypt. So what she does is she takes Bob's public key, which is 4, and puts it to the power of 13 by her private key, followed by mod 89, and she gets 16. So now they both have the encryption key. Mind you, this is the same concept that my team member explained earlier, the Dipole-Hellman key protocol concept, where they essentially get the same key without physically ever transferring the same key by using some logarithmic equations and whatnot. So now they both have the encryption key. So in order to decrypt the actual ciphertext, Alice will need to take the inverse of that key. So she does, and she gets 39. So now the decryption key she has obtained. So to decrypt the actual message itself, she multiplies the decryption key by the ciphertext, which is 26, followed by mod 89, and she gets 35. So now she has successfully encrypted the message. So for demo purposes, we created a script to make it easier to follow a little bit. We'll be explaining the documentation behind it, and then I'll be putting it in action. So first, we have the public key and private key generation, and they both take 3 parameters. For the public key, we have our prime number, we have our alpha, which in other words is our prime generator, and then we have large B, which is our private key, right? Which is in the example that I just explained would be 4 for Bob. And then for the private key, we have the same thing, right? Prime generator, we have our alpha, which is prime generator, and then we have our public key, which is, in the example explained above, is 8 for Bob. So again, right here, it just explains it. P is our random prime integer, alpha is our prime generator, public and private keys. So the main script, it takes a few arguments. So say we want to encrypt the message. We have our P, our prime, and we have our alpha, our prime generator. We have B, our private key, and then we have the message we want to encrypt, which in this example uses 44. And then VV, I just did it as an option, whether you want it or not. So we don't have to include it, but it's just like a verbose. It gives you like, it pretty much lays it out in pretty text for you. So we look at the example here. We input, I guess this works. So we input the information that it asks of us, right? So our plain text message right here is M, which is 44. So then the key is created, which is our prime, our alpha, and then the share key. With this, it encrypts the message as 73, right? So that is now our ciphertext. So what you can do with this is now Bob could send the actual key, which is the imperial key, which is 13, along with the ciphertext, which is 73. So that is formulated. Let me close this tab. So then going back to Alice's shoes, say we want to decrypt the actual message. She would pretty much input like all the same arguments, which is using the same prime number, of course, 79, the same prime generator or alpha, which is 30, and using her public key or her private key, I'm sorry, which is 61, and then the message and the ciphertext that is encrypted, which in this case was 73. So we look at the output of it, and it lays it all out for you, prime, the generator, and the share key. So with this information, she pretty much decrypts the message 73. She encrypts the message 73 and gets 44, which was our plain text. So I hope that helps understand a little bit. So now we can look at the script and you can see it in action. So here's our arguments pretty much, but that's not what we're trying to worry about. So let me just collapse some of this. So the main ones we want to look at is the encryption and decryption, right? So here we go for the encryption. Again, as mentioned, it takes 3 arguments, right? Our prime, our alpha generator, and then our public key. So in order to generate the private key, we do a little bit of math. We take our prime generator and we put it to the power of our random private key, as explained in the example, followed by mod prime. The encryption key is then made by taking our key and putting it to the root of R, which is again our private key, followed by mod 9. So now we have the encryption key, right? So now to cipher the text, we would have to get our encryption key, multiply it by P, followed by P, which in this case would be the message, multiplied by mod P, which is our prime.
Rene, I don't think we could see your actual script right now.
Oops. Let me see. You guys can see my my Google tab only?
Yeah, that's all that's showing.
Okay, let me just open it on GitHub. Give me 1 sec. Sorry about that. Okay, you guys can see it now, right?
Yes.
All right, thank you for that. Okay, again, in verbatim, first to encrypt the message, we did a few calculation, like the calculation equation, and to create the private key, we'll take our alpha generator and square it to the square root of R, which is Bob's private key, followed by mod P. Then the encryption will be made using the private key, sorry, the public key squared to the power to the R, which again is a private key, followed by mod P. To cipher the text, we use the equation of the encrypted key multiplied by the message, followed by mod P. So then Bob sends this, which is sends the key, followed the key and the ciphertext, right? So Alice gets this and she wants to decrypt. Here's the calculations for that. She would first get the shared key, which is the public key, power to S, which is her private key, followed by mod P. And to decrypt the actual message, she would get the shared key and take the inverse of that, multiplied by the actual ciphertext, followed by mod P, and she would decrypt the message. So if we run an example of this, let me try to figure out how you guys could have seen my terminal. Can you see my terminal?
Yes.
Awesome, thank you. Let me just go to the root directory folder. Okay, so if I take the example showed above, let me just pull that. So we're gonna encrypt the text, right? So here is the commands for that. Python is pretty much our main script. Well, that's the decrypt text. Give me 1 sec. Okay, here it is. So we want to encrypt the text, right? We have our prime set as 79, our alpha set as 30, our private key set as 59, and the message you're trying to encrypt, which is 44. So again, just as explained in the example above, we have our we have our plain text, we have the key set, we have the empirical key generated, and we send this information to Alice, which is the key 61 and the ciphertext 74. So now say we want to decrypt this. Again, mostly using the same inputs, which is our prime, our alpha, the keys, and the ciphertext. Alice then gets this key from Bob, and she can then decrypt, which she gets 44. So that's our running example. Let me see. And now my teammate will take over the rest of the slides.
Yeah. My name is Anthony Spencer. first, we're just going to go over a couple attacks on El-Gamal. One of the attacks we're going to go over is just the plain brute force attack, and then the next attack is going to be the man in the middle attack. And then for the brute force attack is if we create M and then M prime with the same values. As you can see, C1 equals Km mod P and C2 equals K and prime mod P, which gives C1 over C2 equals M over M prime. Hence the need to exchange the values A, P, R, and X each time. The search for brute force is pretty exhaustive. It's going to be a lot if you go to the next slide. Yeah, I have the given a 64-bit key session, and if n is 256-bit, O would take about 2 to the 256, which, as we've seen in a different presentation earlier, is incredibly long. The second is searching for all possible encryptions for all possible messages. This, with the same parameters, would be 2 to the 64 times n minus 1, which would take 2 to the 320. It would take even longer. So the brute force attack is not really feasible when it comes to El-Gamal. And if you continue. The man in the middle attack, this is where attacker gets between Alice and Bob and intercepts the key G to the A sent by Alice and sends Bob another G to the A key, intercepts the G to the B sent by Bob to Alice and sends another G to the B key. The attacker thus then communicates with Bob and Alice using the shared key G to the AB. Bob communicates with Bob using their shared key G to the A prime B. The workaround for the man in the middle attack is using a hash algorithm to exchange for the value exchange A to the X mod P and A to the K mod P. A prime number of the order of 300 digits as well as R to the X of the order 100 digits are quite simply pretty much impossible to break. There is no efficient algorithm to solve discrete logarithm problem of finding two values X and R. XR equals log A to AK, having in possession AX mod P and AR mod P. This is the conclusion for more than just the attacks, but El-Gamal for encryption is twice as slow as RSA, but it's actually faster than RSA for decryption. So it's kind of use case scenario there, which one you're going to use. The size of the encrypted data with El-Gamal is twice as much, and the complexity of the El-Gamal algorithm is 2 to the log n, and RSA which is n to the k. So it's kind of iffy on which one is better. When researching this, all the forums, it's kind of like Coke versus Pepsi. People just keep arguing about which one's better, RSA or El-Gamal. So it's not really fully decided yet. And if we go to the next one, real world uses. Real world uses, most of the time El-Gamal is used for slower speeds smaller messages because of its slower speeds and the way it increases the size. So smaller messaging systems tend to use it, but what we have actually seen it is electronic voting. And then also variants of El-Gamal are used and all over the world and is included in the DSA digital signature algorithm. If we continue. Helios online voting systems. This is a internet web-based voting system that's used by unions, committees, and universities to elect student governments. They use actually El-Gamal encryption for their open source voting software. And if we go to the next slide, the DSA, digital signature algorithm, although it's not completely El-Gamal, it is a variant of the El-Gamal crypto system. The NSA developed it and called it the digital signature algorithm. And in 1990, or they developed it in 1991, and in 1994, NIST officially added it to the standard in FIPS publication 186-4. And then these are just our references. All right, so thank you.
All right, great, thank you. I like that you provided two attacks on the El-Gamal, and also you compare El-Gamal with RSA, so that's great. So I have a quick recommendation or suggestion. When you're explaining the algorithm with source code, the fonts are too small for us to see, at least from my screen. The commands and the fonts in general too small for me to tell what's in there. But the effort is really nice to understand the algorithm process with an example, numerical example, and also with the function or actual program. So that's great. So let me think. I think there is one general question, which is, because in the explanation, I heard that there are multiple parameters in the El-Gamal, right? In El-Gamal, and more than RSA. But can you let me know one maybe parameter or one key or one thing that's used only once, or it's gonna change every time? And also one parameter that's gonna be the same for the same pair of sender and receiver. Because let's say for RSA, if we use our public key and private key, we generate that key pair, right? And we can keep it actually to use multiple times. That's what we usually how we use RSA keys. But how about El-Gamal? I'm just wondering, is there anything similar like RSA keys that we can use for a longer period of time for the same pair of sender receiver? Or is there anything that's gonna be one time only?
Yeah, so it kind of has a little bit of both. So like say so you said something that stays the same, right? So that'd be like the private key, where like Alice and Bob like select the private key. Like that key itself is used to like calculate the other equations to make the shared key or the empirical key. But so the public key though, and like in another sense, that's what's like being sent back and forth. So that's where like the man in the middle attack comes in. So say like Bob calculates his public key and he sends it over to Alice. Like say he gets lazy and he wants to use the same public key. I mean that an issue then arises because that could be like a middleman attack could like get hold of that key and then use it like for malice intent.
Yeah, because I remember in your example there is a for Bob, I guess there's a number 4, right? So is that one time or is that a multiple times?
Yeah, so that's a one-time use. Okay. Well, actually, yeah, depending on the ciphertext, if you wanted to encrypt something else, then a new one would be created. So, yeah, it depends on like what you're trying to cipher at that moment, or what you're trying to decipher later on. So yeah, again, like the private keys, like what stays the same a majority of the time, and depending like if you want to encrypt something else after the fact, you would use a different private key, which was Bob's, or the one that you just said, which was number 4.
Okay, because I think there's some misunderstanding there. But in El-Gamal, there is a random number generated, which is maybe more or less the private key you mentioned, right? And that
Yeah,
is
the private key.
Yeah, that's definitely one-time usage. Even for the same plain text, we always use a different random number each time we encrypt it. But I think overall you got the algorithm down. It's kind of more complicated though. Thank you very much. All right, so let's move on to number 4.